Okay. Whoops. Let's start my video. If you're from Chicago, you may know Steve Goodman, because Steve Goodman was from Chicago. Let's see. I'm trying to do my thing so everybody can see me. There we go. I'm gonna move it over a little bit. Pad of paper. There we go. With a pad of paper. I'm gonna share my screen though because I have the notes. So let me share the screen and then let's see. We got 70 people. Shruti, are you there?
Yes, Dr. Jobwood. Hi.
Good morning.
Good morning.
Okay, we have 5 weeks left. We're 2/3 of the way done. We're going over advective dispersive flow. We just finished up the Streeter-Phelps equation and plug flow in streams. Plug flow in streams doesn't have to be the Streeter-Phelps, but Streeter-Phelps assumes plug flow in streams. Your homework is due today. And so I'm going to post another homework in the next few days before Wednesday, okay? So look for the next homework. Today I'm going to go over how do you do a control volume with dispersive flow. And so I'm going to share my screen again. And I'm going to move over if I can. Let's see. I have it here. Oh, yep, this is it. Fick's law of diffusion right here. So this is advective dispersive systems. This first page, water quality modeling, derivation of the advective dispersion equation. E here is a dispersion coefficient, so don't get confused. It's the same thing. This is Fick's first law. And this first page goes through this whole process, but I'm going to do it by hand because this gets a little messy. And really, it boils down to this equation. If you assume steady state, dc dt equals 0. If you assume steady state, this is you have this term is an advective term. Advective flow is velocity. Q over A is this is cubic meters per day divided by area gives you velocity. So that's like a stream velocity. Over here, this is the diffusion term, and then you have reaction. So we have advective flow, diffusive flow, or excuse me, dispersive flow, where E is the dispersion coefficient, and then reactions. When you simplify this, you get these two terms. This is a second order differential equation, first order. So this equation's been solved. There's whole journals basically dedicated to problems like this. Mathematicians have a heyday with this equation because it's often, you can solve this equation by setting this equal to 0. It becomes an ordinary differential equation, but it's a second order ordinary differential equation. And it takes some trickery to solve it, but it's easy to solve analytically, but also we can solve it numerically by different means. And we're not going to go into any of the numerical methods to solve this, but just know there are. It boils down to what we talked about before when we were talking about dispersion across compartments, where we have a cross-sectional area A, and we have a dispersion coefficient D, and a concentration gradient from the center of one compartment to the other compartment. and J again is our diffusive flux. So we're going to talk about the unit. Well, it's mass per time. We're going to talk a little bit about the units there, but this is our advective term and so let's go through this equation. I'm going to write down this equation because this is basically our accumulation equals inputs minus outputs plus or minus reactions. We have a advective inflow, we have a dispersive inflow, we have a advective outflow, we have a dispersive outflow, and then we have reactions. And in this case, I've just written it as a first order reaction term. I'm not going to have you derive any of the math here like we did with the Streeter-Phelps equation that you should be able to derive. And in some cases, you've kind of had to do some of the homework problems because you had to use the integration formula to solve some of those problems. Here, I'm just going to present it so that you understand it a little bit. When you simplify it, expand it, you get this equation. So let's stop sharing and let me write it on the paper just so that you see it. We have here now a control volume with C coming in and C plus delta C going out. That's our diffusive, or that's our advective flux. We have Q coming in from here. We also have a dispersive flux. And I'm going to move my screen so that I can see what I'm doing here. We have minus, and I'll use a D for our dispersion coefficient, area times change in C over change in distance. This is a diffusive flux going into our system. And then our diffusive flux going out of our system is a little bit trickier because it is minus D times A and times the change in C over the change in distance minus D times A times the change in the C over the change in the distance. So we have a change here. Just like we put a delta in front of our C here, we have to put the delta in front of our change in this. This, again, one way to look at it, and I'm going to write it on a separate piece of paper here so I don't mess up this piece of paper, is you have a slope going into this point. And so over 3 points, you have a change in the slope. Here we just have, with advective flow, we have a change from here to here to here, such that this point is going to reach over here pretty soon, and we're going to get an increase in concentration. If we have a conservative chemical, and there's no, because this is our flow is going in this way. So this is at x equals 0, this is at x equals L, some length profile. And if we've got this concentration gradient in our stream, the concentration at this point is eventually going to reach this point, and this concentration, which is low, is going to go up. So our change in concentration here is positive because of the gradient we have of concentration within the stream. The diffusive flux is because of the change in the concentration gradient. So here you have a change in the concentration between here and here. Here you have a change in the gradient, a change in the slope. It goes this way and then it goes this way, okay? So what is going out here then, at this point over here then, when this reaches this, the concentration at the middle is going to go down because this point is higher than this point is lower. So by diffusion, that point should end up being lower. So this is our flux due to our change in our gradient around this point. And so we have the same gradient at this point, but we have to add a change in that gradient. So it's the same concept that we have here, only we do it here. And then we have plus or minus reactions in this control volume. So our accumulation term is equal to inputs minus outputs plus or minus reactions again. Our accumulation term is dc dt. It's always as a function of time, times our volume again, because this is now mass per time again. Our inputs are these two inputs. So we can deal with our advective input and output if we want to first, and then we can deal with these. So if we deal with our advective input, it is just Q times C, because Q times C gives us our mass per time going in. That means that to do this term, right, we only need this term in here because this is mass per time. Remember our flux, J up here, J is equal to minus the dispersion coefficient times the cross-sectional area times the concentration gradient from this point to this point across this cross-sectional boundary. So we have C1 here, we have C2 here, and we have some flux through this area. And remember, this area could be square centimeters. This dispersion coefficient is centimeters squared per second. This is concentration, which is moles per centimeters cubed. If I keep it all in centimeters, divided by distance, which is centimeters. Okay? So this is centimeters squared, centimeters cubed, divided by centimeters cubed gives us centimeters in the numerator. This is in the denominator, so we move it up and it cancels. So all of our centimeters cancel with each other. Moles per second. This flux is in mass per time. Okay? That's what this is. This is mass per time. This term is mass per time too, which means we don't have to multiply anything by this. We just have to write it. And again, this term from before is Fick's first law. It's simply Fick's first law of diffusion, but we're using it as a dispersive term because in this case, the D is a dispersion coefficient, okay? Because we've got dispersion occurring across this boundary. We have dispersion occurring across this boundary. So these two are our inputs. Our outputs then are minus Q times C plus delta C. And then our other output is this term. And it's minus this. So when we minus this, it becomes plus and plus. So we can say plus dA, dC, dx, plus d times A times delta dC dx. And we know that this term cancels with the first term here once we multiply this out. This term will cancel with this term because they're exactly the same. And if we put on, well, I'll just put on a reactions here so we have it, plus or minus reactions. So we have a reactions term here. So now for our advective flow, we have minus Q times delta C. And then for this term, we have plus dA times delta dC dx, plus or minus some reactions. This is dC dt, and I'm going to divide now by volume. Okay, so I think you can all see that. For some reason, my light isn't very good here. I don't think that helps it, but I think you can see it. You can lighten your own screen, I guess. So this is what we get for our, in this term again, is advection. It's basically water moving from one place to the next. Again, it's like putting our rubber ducky in the river, and then our rubber ducky moves downstream because it's moving at the rate that the current is moving. If we put 10 rubber duckies in the stream at the same time in the same location, this term causes some to move faster and some to move slower because it's our dispersion term. But now we have a cluster of them, and the highest concentration is towards the middle of that cluster. So this is our dispersion term. And then we have our reactions. Okay? We could, again, set this to 0, but we won't do that quite yet. V and Q we have to define. Again, Q is our average velocity times our cross-sectional area. This is meters per second. This is area. Meters times areas gives us cubic meters per second, which gives us a flow rate. Our volume is our cross-sectional area times our change in distance here. Because up here in our little, I didn't write it here, but from here to here we have delta x because we have a change in distance from this point, from this boundary to this boundary, we have a change in distance. Okay? So now we can substitute a few things in here and simplify this. If I do that, I get dC dt is equal to Q is flow rate times area, volume is area times delta x. This is dC. So I put in my V is these two, my Q is these two, and my delta C is my delta C, and that's where we get dC dx. This and this go away, and our first term here, and I have to put a minus in front of this, our first term here is minus average flow rate times dC dx. We'll make this a partial differential equation because it's a function both of time and distance, okay? This second term now, right here, is our diffusion coefficient is the same. So plus the diffusion coefficient, we have an area, we'll leave that as area, but our volume in the denominator becomes area times delta x. And we have two D's here, basically a delta C over delta x plus our reactions. You often wonder why they write these second order differential equations the way they do. The A's and the A's cancel. We're left with a D. This is a delta delta. That's delta squared. times C. This is a delta X times a delta X. That's a delta X squared. Hey, that's where all of that, the why you put the square on the delta here, why this whole thing is squared, okay? Plus or minus reactions. This is advection and dispersion plus or minus reactions. So this is our dispersion term. It's a second order term, and it is in the notes, but we'll talk about it a little bit more. But I basically, on this one page, and I'll upload this one page because it may be a little clearer from the rest of the notes, but it basically explains how you derive the overall advection dispersion equation. This equation is used in any stream that has significant advection and dispersion, and that also includes estuaries. So in these notes, we go over estuaries. We're not going to go over estuaries too much in this class, but we are going to see this again because in groundwater, the water has to flow around particles, around sand grains, around gravel particles in an aquifer. And so we also have dispersion occurring in an aquifer. We also have to add one more thing in an aquifer because we have another reaction occurring in this control volume, and that's adsorption. So we have the chemical coming in, and it can either keep on going or it can adsorb to the particles, and then it gets slowed down. Its movement gets slowed down because of adsorption and then desorption off of the particles. So, and that's also true in even if you've done any analytical chemistry with organic chemistry. If you use an LC or a GC, a liquid chromatograph or a gas chromatograph, you have a column that has either particles in it in the case of an LC, or a film on the surface of the capillary GC column, and the chemical either adsorbs to the solid media or it absorbs to the surface of the capillary, and then it absorbs and then desorbs as it moves along. So the compounds that absorb the most come out at the end. The compounds that absorb the least come out really, really fast out of the column. And so you can separate out columns by their different affinities for adsorption in a kind of system like this. You do get some dispersion of the compounds as they're going through. So you see peaks. They don't just come out as a sharp peak. They come out over time. And sometimes you could push those peaks to be really, really sharp. If, for example, for an LC, if you run a gradient with solvent, you can force that peak to be very sharp. For a GC, if you run a temperature program, you ramp up the temperature, and then you can get really, really sharp peaks as they're coming out. So there's different ways to do that. Let me go back to the notes. Unless anybody has any immediate questions. Okay, let me see. Share. Okay, so we're back here now, and I basically just derived this equation. The only difference is in this equation, I have a first order term here, minus k times c times v, which when we divide by b, we just get minus k times c. And I've got an e here rather than a d. So I've let the e represent the dispersion coefficient rather than the e. This is a linear, non-homogeneous second order partial differential equation because concentration is a function of time and a function of distance. It's the advective dispersion equation with constant cross-sectional area, constant flow, constant dispersion coefficient, okay? let's talk a little bit about estuaries now. I will talk about estuaries. Before I talk about estuaries, let me share one other webpage with you. Anybody tell me what boat this is right there? Unmute yourself and tell me.
Is it the boat in the Suez Canal?
Yeah, this is the Ever Given, which is the boat that was stuck in the Suez Canal. So this webpage is what? Marinetraffic.com. If you go to it, you can track all of the thing. The boat was stuck right about here in the canal. And all of these are littler boats that are like tugboats that were helping it. They're not big boats. They haven't sent any big boats. It was stuck right about here. So I think they're waiting until it gets out completely until they send some of these other boats in. All of these boats are obviously waiting to go. They're circles because they're not moving yet. So they're waiting for this boat to clear. And then you've got a couple up here. And then you've got all of these boats sitting out here in the Mediterranean Sea right outside of Cairo. Here's Cairo's right about here. Nope, it's Cairo's back here. So you got all of these boats. Some of them are moving like these, but some of them are sitting here. So what's amazing is if you track boat traffic, here's all of the boat traffic, and now it's moving again through here. But there's a lot of traffic around the Cape, and it used to not be this way. All of these boats would have been going through this canal in general, unless they were going over here to South America. But there's a lot of traffic going around the Cape and then up to Europe and up towards the US. So by cutting this off for about a week, it really, really slowed up traffic to the point where I think Syria doesn't have any oil anymore. So you guys get the idea. So it's amazing. You can study dispersion of boats in the oceans even. There's a ton of boats all over the place. If you go up, we can go over here. This is kind of a fun web page, but I don't want to waste too much time. Even boats in the Mississippi River. There's lots of barges in the Mississippi River. If you go over to New York, though, here's, whoops. I'm not quite there yet. Here's New York City and boats going to New York. So anyway, marinetraffic.com. There's also web pages like this that do air traffic. So I've been in airports where we've looked at planes flying in, and once an airport closes down, the skies like go crazy that all of a sudden nothing's there. So here's our estuary. We're going to do a tidal river and an estuary. What's the difference between a tidal river and an estuary? Anybody know? What do you think it is? Rivers are made out of what kind of water? Starts with an F.
Well, rivers are made out of fresh water, and then isn't an estuary kind of where like the fresh and salt water mix?
Exactly. So out here is the open ocean. An estuary has a gradient of here at this point of very low salt, because above it is the tidal river, which is basically fresh water, no salinity. estuaries have salinity in them, but they range from the ocean water to the river water. So an estuary is the boundary between the ocean and the river. And this boundary actually changes because at high tide, this boundary moves up, and then at low tide, that boundary moves down. Okay, we're having fun now. So tell me about tides. How high do they get? Bay of Fundy. Here you go. There should be some nice pictures of this. Oh, here's a YouTube video. Well, I don't want to see
You
this.
can see exactly how fast it's actually moving, and just bringing all the tide in. So the tide doesn't come up fully for another hour and a half. So
This is a low tide. Okay.
remember,
This is at high tide. Although that's not that great. I think it's more like during part of the season, it's about 20 feet. There we go. So we were right about here. You can see it's drying out actually. It was up here. Most tides are not that extreme, but this is one of the places in the world. This is in Canada on the East Coast. In north, you could go to maps. And show you where this is. Bay of Fundy is up here someplace. There you go. Right here. Here's St. John's. So it's in one of these seaports where they did that. I think up here too, but that was probably in St. John's. Well, I don't want to be in the town. I wanted to be on the ocean. St. John's River. We'll go right to the thing. There we go. So it's not in St. John's, but it's close. It's close to this location. And here you can even see the tide is out quite a bit. That's at least 10 feet from that point to that point. So Bay of Fundy is known for its tides. So getting back to this, tidal estuaries, and that's an estuary system because you can see the marine water going up and then it goes back out. And there's constantly fresh water coming down. So the estuary is where you have the salinity less than the ocean water, but greater than the river water. Okay, so if we have a point discharge, a waste, like right here, coming into this tidal river, so if we have a discharge point at this point, and of some chemical, at that point, you get some of the chemical going upstream, the chemical going downstream. This is assuming that it would be a first order decay process. Because if it wasn't a first order decay process, you'd actually have a higher concentration down here and a slightly higher concentration up here. Salinity gradient, though, starts where the tidal river and the estuary start, and it goes up, and then once you hit the ocean, it's a constant value. So this is almost like a first order growth curve here. So you have a salinity profile within the estuary with very low salinity in the river, high salinity in the ocean. And to get from the one to the other, it's actually like a first order growth profile. Variations with time, here's stage. So low water slack time, high water slack time. This is time. And so the water stage, and this is what we were just seeing in the Bay of Fundy, the water elevation in the estuary or the tidal river goes down. And it's a tidal river because this estuary water is pushing this river upstream. So the water in the river actually rises because you got water coming down and water coming in. And so what does the river do? It actually goes up, but it doesn't mix with the estuary water. It still is part of the tidal river portion of the water. It's just that this estuary water is pushing the water back up the river. And so you, even in the tidal river, you get tides occur. You see these tides occurring because the water goes up and the water goes down, but it maintains its freshwater status. So the tide goes down and then it goes up. What creates this tidal cycle? It is here, it is written here on the sheet. If you look carefully, hold on just a second. Hold on, where am I? Okay, let me share again. Okay, so tide, what causes tides? Did I unmute myself?
The moon? You didn't
The
unmute yourself.
moon, yeah. It always amazes me the number of students sometimes that don't realize that because you don't think about it and nobody told you. But what causes tides is the gravity of the moon on the Earth. The moon is a large object that circulates the Earth 12.42 hours. Every 12.42 hours we have a tidal cycle because, and it also occurs at this cycle because the Earth is going around and the moon is going around the Earth, okay? So I'm not quite sure, it's not the moon necessarily going around the Earth, but the Earth is spinning on its axis and the moon is out, and I don't know how fast the moon is going around the Earth, but it is. And so a combination of those two sort of spinning cycles creates these tides. And so we actually have some tides during the year that are larger because of the moon and the sun aligning, because the sun also has some gravitational effect on the Earth. So you do have a maximum tide during the year because of the sun and moon aligning, right? But the average tidal cycle is 12.42 hours. So it's not a day, but it's close to a day. So if you're staying in Florida for a week and you look at the tidal cycle, it's about the same every day because it's on this close to 12-hour cycle. Okay, so you go out one day in the morning, if the tide's out, the next day tide will be the same place. Okay. The current velocity then, if you look at any place along this tidal river in this estuary, if I'm at high water slack tide, that means the water is it's kind of like not moving. And here the current velocity is 0. But since it's high water slack tide, after that, the water is going to move and it's going to be positive. It's going to go towards the ocean. So here we're in ebb cycle, and here you're in tide cycle. The tide's coming in here. This is so the tide goes ebb and right. The tide's coming in and then it ebbs, which means it's going out. So at high tide water, high water slack tide, when the water's not moving, immediately after that it's going to move back out to the ocean, and the velocity is going to increase downstream. On the other side, here's a low water slack tide. The water is out, and the water, once the water is out, let's see, as the stage is coming up, that means the water is coming in. That means the tide is going backwards. It's going upstream here. So this curve tells you about the stage at the point along the tidal river or estuary. This tells you the current velocity within the stream during the stage cycle. And then the salinity too. If it's the estuary, salinity is low, but over here at high water slack tide, the oceans come up the most, so you have a higher salinity at that point of the high water slack tide. Okay? Estuaries, primary mechanism of dispersion in the estuary is a salt wedge. It's a concentration of salt from the top to the bottom because if you think about estuaries, you have salt water coming in, and salt water is more dense than fresh water. So that salt water coming in from the ocean, when you've got the tide coming in, that salt water is typically moving along the bottom. And then at some point, you have a 0 point of net velocity. The fresh water then is moving along the top. So you can have a system where the ocean is coming in on the bottom and the fresh water is going out at the top. And at some point, you have no net flow of water. And at that point, you get sedimentation. So you get 0 net velocity. That means, hey, water's not flowing. That means we get sediments and you get all of these deposits. That's how you get sandbars formed in these estuaries because they're always being created. If you know anything about Florida along coastal rivers and things like that, there are always sandbars forming and then dissipating because of these different tidal cycles. Okay, so you end up with turbidity in this system, but the vertical gradient is, hey, at least in the river, moving towards the ocean, but then in the estuary, you get this sort of flow pattern where it's on average flowing along the top downstream towards the ocean, and then it's moving upstream along the bottom because this is the saltier water goes deep and the fresher water floats on top of the salty water. So you get this sort of plane of no net motion where you get deposits occurring. Okay. Don't worry about the math, but in this point, I go through this with my graduate students. So when I teach this a similar class to graduate students, they have to know all of this silly math. But don't worry about it. We won't go through all of the math about here. But just know that this equation then, this equation, doing the Streeter-Phelps equation with this dispersion term in, we still have L and D for on L and on deficit. So we can actually do a Streeter-Phelps analysis using the diffusion term within our overall Streeter-Phelps equation and solve for it. And so that's what I've done here. I've solved basically a Streeter-Phelps type BOD and deficit equation with these are our normal terms in the Streeter-Phelps equation. Well, all I've done is add diffusive terms in for BOD and deficit here and solve for it. And this is basically the solution. And we won't talk about it, but it ends up becoming a nasty equation, big nasty equation. But here's what it looks like. So I think that's all I'll cover with this. But the take-home message here is this equation then is accounts for advective flow and dispersive flow and then reaction. And we can make this zero. We'll reevaluate or we'll revisit this equation with adsorption in for groundwater systems in a little while. But at least I got to present the derivation of this equation, and we got to talk a little bit about tidal systems and mixing in tidal systems. Okay? Any questions? I think we have just about everybody here today. Groundwater systems are kind of fun, and we'll start those either probably on Wednesday. Okay? Okay, I'll let you go 2 minutes early. I'll see you on Wednesday then, unless anybody has any questions.
I have a quick question.
Yeah.
Do we know when we're gonna get our other homework grades in by chance?
Shruti, how well are you doing on the grading?
I'm finished grading homework 2 and 3, but I'm yet to total them up to post it. I should have them by tomorrow night for homework 2 and 3. Is that okay?
Yep.
And then homework 4 was due today. A few people are turning it in late, but it should probably be posted by next Monday, probably, I would assume then. Okay, we'll see you guys.